Hello everyone, I'm William Fines-Kested. I'm a student at the Massachusetts College of Liberal Arts. Before I start off my presentation, I'd like to thank Archer, Sarah, and Ruben, who are graduate students that I worked with, as well as Dan Lathrop, whose lab I worked in this summer. So my talk is titled Predicting Experimental Chaos with Reservoir Computing. So the big thing that we should cover first is what a reservoir computer is. So the simplest explanation of it is that reservoir computing is a form of machine learning. So we take some input data on the left, f of t, we apply it to the reservoir, and as it's fed through it, we read it. That produces some output, f of t plus delta t. So we're looking at this output to see if it matches to the next data point in our f of t. And this reservoir is interesting because it seems to perform better with dynamic systems, so things like the weather, or speech recognition, or financial forecasting. When we are ready to start making predictions, we take this f of t plus delta t and feed it back in as our original data. We predict for as long as we want, and then we compare the original data and the prediction. So what my focus was this summer was on one chemical reaction called the Belousov-Jabotinsky reaction. On the plot here on the left, this is just the first 10,000 data points of 65,000 data points, where we are looking at how much bromide is in this reaction over time. So this time series that I have was originally collected by a team in the University of Texas at Austin, and I feed that into my reservoir computer with some initial parameters I've chosen heuristically, and from there we minimize how much error there is by changing the parameters of the reservoir computer. So this is the first prediction, and probably one of the nicer predictions that we have. On the top we have the prediction in red and the original data in blue of the bromide concentration over 700 data points. And the graph below is the error between the two. So you can see that we have a lot of regions where the error is very low and some where it's not. For this first range of 200 points, we have a fairly strong prediction, where in other regions we also have a very low error. But one of the issues that we run into with these shorter predictions is that the predictions can start to fail out, where we have some erratic behavior and a jump to something like 120%. So the prediction at that point and at this range is no longer worth looking at. So we can always push this back, but what happens when you do that is that you kind of start to increase the error earlier on in your prediction. So you kind of have to choose whether or not you want a very short, accurate prediction, or if you're willing to look a little bit further, but also introducing a little bit more error into your prediction. So that's one aspect of the research. The other is understanding the behavior of these chaotic systems. So with this Belousov-Jabotinsky reaction, it has a dependence on what its initial conditions were. We can try to make what are called climate models of these very long data sets that we have to try to understand better the mechanisms by which this chaotic system is behaving. So we can't predict long-term what's happening. It'd kind of be like me trying to give you a day-by-day forecast of the weather 2 months in advance, and you shouldn't trust me if I told you what that was. So we can try to understand the behavior. I can tell you that it'll be, hotter during the day, colder at night. I don't know what the average temperature is in September here in Maryland, but we can, go back and look at past data that we have. So one of the things that we can do to understand these chaotic behaviors are what are called return maps. So on the horizontal axes, we have the local minima of our data, and on the vertical axes, we have the point immediately following the minima. And what this is characteristic of the data set that you get these plots from. So up top, we use the original data, and there's a few key aspects of it. We have kind of like a density in 3 regions of the original data that we see in our predicted data as well. Of course, the return map for the predicted data isn't perfect because we have these noise in the top left and far right. But this is a fairly good prediction that can tell us a little bit about what the dynamic system is doing. So as for future steps, there is a second set of Belousov-Jabotinsky reaction that I can work with. It'd be interesting to see how the same kind of chaotic system behaves with the parameters that we had originally versus what we'd have to use to optimize for that data set. There's also, we can do prediction mimicking of velocities of particles in turbulent flow. And lastly, we could calculate Lyapunov exponents, which are more characteristics of chaotic and dynamic systems. And then once we calculate those, we can compare them to the known and calculated ones from our original data sets. So with that, I'd like to thank you all for coming to this talk, and I hope you enjoy the rest of the talks today.